All right. So we are starting section 4B.4, area and determinant of a matrix. The overall objective of the section is to interpret the determinant of a 2x2 matrix. Yes, I think so. Geometrically. So part 1 is what you got today. It's also part 1 and part 2, but doesn't matter. Determine the area of the image of a unit square. We're going to apply a given linear transformation to a unit square and determine its image. And then from there, we're going to see what patterns we find. So first practice that we have here is we're going to draw a unit square, okay? A unit square is comprised of only these 4 vertices, 0, 0, 0, 1, 1, 0, and 1, 1. So we're going to go ahead and draw that little baby here. Okay, so that's our unit square. What would be the area of this unit square? 1, right? The area would be 1 because it's 1 times 1, which is 1. It's called a unit because it's 1 unit square. Okay, so we know the area of this is 1. Agreed? All right, we're going to be manipulating this little square. All right, if you have 3 other colors to use, ideally that would be great for your notes. If you don't have 3 other colors, it doesn't really bother you, cool. But if you do want to grab 3 color pencils, they're on the supply card. It's just because we're going to be drawing, well, 4. Yeah. We're going to be drawing on top of things. So if you want the color, cool. If not, you don't have to have it. Does that make sense? All right. So next what we're going to do is we're going to transform that unit square and see what it produces, okay? So up first, we have our first transformation, which is 2, 1, 4, 3, which means 2x plus 1y and 4x plus 3y, right? And we're going to transform that image. So yesterday, we talked about how to transform multiple points at a time, correct? Not yesterday, Monday, we talked about how to transform multiple points at a time. And the key thing here is making sure that you are putting them all into one matrix and keeping your x's and y's paired vertically. So for example, with number 1, if I want to find the image of the unit square here, I have 2, 4, 1, 3, and then I'm going to have 0, 0, 0, 1, 1, 1, and 1, 0, right? Because those are the points that I'm transforming. And then to find its image, all we're doing is multiplying, correct? Yeah? Is that making sense? Ringing bells? Okay, so then we're going to set up the next ones, and then you're going to go through and multiply so that you can then tell me what the answers are. So let's finish setting them up, and then I'm going to give you time to talk to each other, work it out, and multiply. Okay, our original coordinates are going to stay, vertices are going to stay the same. And we have 3, 2, 1, 4, and 0, 0, 1, 1, 0, 1, 1, 0. All right, you guys are going to go find my image. So I'm going to give you time to multiply. And you can multiply by whichever means you choose. So whether you decide to multiply by calculator, by hand, or by Desmos, it's up to you. Hello? 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 All right. What were my images? For the first one, what we get?
Horse.
We did not get horse. Anyone with real answers? So we have 0, 1, 3, 2, then 0, 3, 4, 7, 7, 4. Okay. All right. I think I put mine in backwards. I did earlier this morning. All right. Next, 0, 1, 5, 4. And then 5, 2. Perfect. And then was RJ the only one that did it, yo? No one else did it?
I did.
Okay.
But, I got fucking so I was looking at the shape.
Oh, the shape is fine. The important part is making sure you can plot it.
0, 1, 5, 4, 0, 2, 5, 3.
Okay. Is that no?
Yeah, 5, 3.
5, 3. I was like, I don't think I got that. I have 1, 0, 1. I have 0, 1, 2, 5, 3. Is that? Yeah. Okay. All right. And then first row, last one. And perfect. All right. So these now represent the new vertices of 4 different quadrilaterals, 4 different ones, right? So what we're going to do now is we're going to plot them. So when we're going to graph, we're going to describe what's taking place, what's the area of each one, and going from there, and we're going to compare. So the first one up is our, I'm going to change my colors. So we're still at the origin. That's true to form of linear transformations, right? And I had 2, 4, 1, 3, and 3, 7. Is that correct? All right. This may not look like a quadrilateral, but it is. It's a very, very skinny parallelogram. And I'm not very good at drawing straight lines, as y'all can see and know from previous experience. So pretend that these are the straightest lines you've ever seen. Boom. Okay. So that's a parallelogram. It's 4 points. A little lopsided, a little struggle. What makes it parallel are the sides are parallel to each other. Okay, now I'm going to do my next one. My next one was 0, 0. This time I'm going to go 4, 2. Then I was still at 1, 3. Then I was at 5, 5, right? So we have and all right. It's a little bigger of a parallelogram. Thank you. And then our third one, so I'll do it in black. All again from the origin. 4, 3 for me. Then 1, 2. See why I said you may need different colors?
No, I'm diagram myself.
Oh, yeah. Just tell yourself it's perfect. That's what I be telling myself. Like, girl, you did so good. Okay. And then my last and final one. I'm at 0, 0. Then 3, 1, 2, 4, and 5. All right. So it's kind of hard to believe that all of those figures came from a linear transformation of a square, right? But the thing is, this square is anchored to the origin, right? So if it's anchored to the origin, all I'm doing is going to be stretching and pulling that square out of shape. Does that make sense? Have y'all ever like tried to edit a photo from one corner instead of doing it from like the sides? And when you move that one corner, it displaces it, right? It's all messed up. So all essentially, if I'm holding this and I'm just changing the other three corners, this is what happens, right? Okay. Not only did they change in their size, but they also changed in their area. Do we see that? The area of each one of these changed. In my elementary school, we had these pegboards with rubber bands on it. Did y'all have those? Okay, I'm old, I guess. We had pegboards and they had rubber bands on them, and you can make different shapes with the rubber bands. I don't know. I wouldn't call it a conspiracy board. It was just a pegboard that my teacher had in the class. And we had rubber bands, and you can make different shapes on there with rubber bands. Well, imagine just leaving one rubber band and moving it to 4 different pegs, 3 different pegs all the time, right? That's essentially what you're doing here. And the conclusion is we're changing the shape and the area. So no longer is it a square, but it's now different parallelograms, right? And finding the area of a parallelogram is not as easy as finding the area of a square. So eventually, a mathematician, someone came up with, there has to be another way. There has to be another way than us trying to calculate. Because in order to find the area of a square, essentially what you're doing is you're taking from here, going all the way out to its highest point, and figuring out the area of the whole thing. So my highest point goes up to 5, 5, right? And so this means if I made a 5 by 5 square, the whole area would be 25. Then I would go through and cut out the pieces. So this piece here is 1. This piece here is 3. This piece here is 6. This piece here is 1. This piece is 3. This is 6. I will add up what I know and subtract to find the area of the other piece. Does that make sense? And that would be me finding the area of a parallelogram. Geometric. Okay? And they're like, man, we can't keep doing that, right? What is something else we can do? How else can we figure out the area of the parallelogram? Is what it came down to. Okay? And what they came up with is it's called the determinant. Okay? I'm jumping ahead a little bit, but it's called the determinant, and it's a way to figure it out. So if we want to find our area, we're going to use what's called the determinant. I always spell this wrong. I'm going to tell you right now. Determinant. I never remember if it's an A or an E, and it just, for some reason, my brain won't allow me to. But the determinant is a very easy process. It involves the linear transformation. And so you're finding the determinant of the linear transformation. And how that happens is you cross multiply and subtract. So we cross multiply and subtract. Does that math sound easy enough? To cross multiply and subtract? Sounds easy to me too, right? So for example, the area of this one, whatever you get here for your determinant, we're going to find the determinant. That's what you're going to multiply your unit area by. So the unit square, the area is 1 unit, right? And whatever happens from here, this is your unit square times your determinant. So for example, we're going to cross multiply and subtract. So cross multiply, what's 2 times 3? What's 1 times 4? And what do we get? 2. So that means we're taking the unit and multiplying it by 2. So what's the area here? 2 units. Does that sound easy enough? Or do you want to do this? You want to do that? You want to draw some sketches and sketch out your triangles and your rectangles? I don't think you do. So really quick, what would be here? What would be number 2? It would be what? 4 times 3. So we cross multiply. 4 times 3 is 12. 2 times 1 is. And so what's our area? 10. 4 times 2. 1 times 3. So what's our area? 3 times 4. 2 times 1. So what's our area? Okay. So how do you feel about being able to find the area of a transformed unit square? Objective accomplished? Yeah. Awesome. So tomorrow I'll give you time to write out the pretty formula, graphic formula if you want to, that it justifies the cross multiplying and subtracting. I know you want to draw this and write it out.